All right, so we are looking at the method of undetermined coefficients, and this is a method that you use for second-order linear non-homogeneous equations. Okay, so non-homogeneous being that there is not a zero on this side. So first, like all of our second order, we're going to need our complementary equation. So that's going to be where we set it to zero, assume that this function over here is zero. It's still the same differential equation on the left. And then in this case, we set y equal to e to the rt, right? And then when you take the derivatives, you get r e to the rt, that's y prime. And then y double prime is r squared e to the rt. And when you plug in, you end up canceling out these e to the rt's, you're left with r squared and simply 4 here next to this coefficient of, next to this linear y, or first order y. So solving r squared plus 4, which is what we end up with, we get r equals 2i, plus or minus 2i. But I just left that out because our general solution for our complementary equation will look like this. So yc equals e to the real part, which was 0, plus c1 constant cosine times our imaginary part times t, which was 2. And then that's the only place that our imaginary part shows up. So we're really just going to have c1 cosine 2t, c2 sine 2t. And that's our complementary equation general solution. Now, the general form of the original differential equation, the y double prime, this original second order, non-homogeneous, is of the form our complementary solution, the general complementary, plus a particular solution. Now, to find the particular solution, we're going to assume that our complementary solution would have been, it's going to drop to 0. So the only thing that's going to be left is the y of p. Well, we assume that whenever that y of p went in, this is what we got out. If that solution went in over here, then this is what came out of it. So it must be some version of this. So we're just going to set it to a times sine of 2t plus b of cosine of 2t. But unfortunately, that is already a solution. Cosine 2t sine 2t. That's exactly what this is. Arbitrary constants times those functions. So we're going to multiply through by a t to prevent linear dependence, which would just make it redundant. So we're going to end up with yp equals t times our assumed solution of a sine 2t plus b cosine of 2t. So we end up with a y prime, a sine 2t plus b cosine 2t plus t times this initial value. I just left it in this form because product is easier to do than all these individual terms. The product rule is easier to use. Now, y double prime did a similar thing. It simplifies to 4a cosine 2t minus 4b plus the product of these two terms. Now that we have y double prime and y prime of p, we can plug these back into our solution, and what we hope is that it is some version factored up by an undetermined coefficient of our g of t, of this function here. So when you plug in, plugging in what we had to our original differential equation, we get a lot of these terms to cancel out. So here was our y double prime of p. Here is our y, so plus 4 times y, because that's what this equation calls for. And we set it equal to what it originally equals. And so, canceling a lot of these terms, we end up with just 4a cosine 2t minus 4b sine of 2t. All these extra t terms cancel, which is great. So we end up with 4a cosine 2t minus 4b sine of 2t. Well, that's exactly some version of what we have over here, which is what we wanted. And it's clear now why we call this the method of undetermined coefficients, because all we're doing is figuring out what these coefficients are in order to satisfy this equation. So now we just set 4a cosine of 2t equal to the cosine of 2t, or you could have just said 4a equals 1. You could just set the coefficients equal to each other, but either way, these cosines cancel each other out, so you're just still going to have the coefficient terms. And so A equals 1/4 and B equals negative 11/4, because I set them equal to each other as well. So we figured out what these coefficients were, and now to the general form of our solution was yp plus yc. Well, we had yc, that was c1 cosine of 2t plus c2 sine of 2t. Our yp is now back to our general form of our what we wanted yp to be. It was t times a sine of 2t, right? It was factored up by t from some arbitrary constants of our original g of t on the right hand side of the equation. Well, now it's 1/4 t sine of 2t minus 11/4 t cosine of 2t. That's the particular solution plus the complementary general solution, and this is the general solution to the whole differential equation. And that is it. Thank you.